Hi everybody, in this video tutorial we'll have a look at how to find the turning points of a function and describe them as maximum or minimum. So let's have a look at the function f is equal to x plus 1 over x. The first thing we want to do is state all the values of x for which we can work out this f. So we want to find the domain of this function, this is how we call it. And here you see that because of this 1 over x, the domain is going to be all the possible numbers, all real numbers, except for 0, because you can't have 1 over 0. Now we need to work out the derivative of this function. The derivative of x is 1, and the derivative of this 1 over x is minus 1 over x squared. So here is our derivative, and if we look for turning points, we want to find points where the gradient to the graph of the function, a gradient which is given by this derivative here, is 0. Because if you have a an horizontal tangent, this means that your curve is making like a minimum or a maximum. So let's solve this equation. We want 1 minus 1 over x squared to be 0. Okay, so we have different ways to solve this equation. Let's just add 1 over x squared on both sides. You get 1 is equal to 1 over x squared. Let's now take the reciprocal on both sides. We get 1 is equal to x squared, because the reciprocal of this 1 here is 1 over 1, which is 1. And so this means that x is going to be plus or minus 1. So this means that this 1 and minus 1 are going to be two critical values for us. So let's draw a number line and see a little bit what's going on for different values of x. So we know that for 0 here, we have a forbidden value, so I circle it in red. We know that at minus 1 and at plus 1, the derivative is 0, so we might be interested to study what's going on like around these 2 points. And because here we've got a forbidden value, we are also interested in seeing what's going on there around this 0. So this means that we need to study our function on 4 different intervals. So this one here, on which x is less than minus 1. We have a second one here, for which minus 1 is less than x is less than 0. We've got a third one here, which is 0 is less than x is less than 1. And finally, our last interval here, 1 is less than x. To do so, we have the choice. One of the easiest choice is to try and factorize this derivative here, 1 minus 1 over x squared, because when you express it as a factor, it's actually pretty easy to tell whether it's positive or negative. So let's try and do that. Let's rewrite this derivative. And this is what I've just done right here. You see this 1 is x squared over x squared, so we end up with x squared minus 1 over x squared. And this x squared minus 1, using the difference of 2 squares, factorizes as x plus 1 brackets x minus 1. Now that we have this factorized form, we can build a critical value table. You can refer to another of my video tutorials to see how to use a critical value table, but here is what we get. You can see that in this critical value table I've used a double bar for 0 because 0 it's out of the domain, so it's to clearly show that this is going to be a forbidden value. And so we end up with f prime being positive when x is less than minus 1, negative when it's between minus 1 and 0, negative when it's between 0 and 1, and positive where it's beyond 1. So what does it mean for our function? Well, if the derivative is positive here, this means that our curve has a positive gradient, so our function is going up. And then it's going down because it has a negative gradient. Similarly, it's going down here and positive over there. So if you look at a very rough sketch, what do you notice? You notice that around here, we should have a maximum because the function goes up and then goes down. So this is what we call the turning point. And here we have another turning point, which is going to be a minimum. To work out the value of this maximum here, we just need to plug the value of x here, minus 1, into the equation for f, into the formula for f, and we get f of minus 1 is minus 2. So minus 2 here is a local maximum for the function. Similarly, we can plug the value 1 into the formula for f to get the value of f of 1, which is 2, so this is a local minimum. It's quite funny here to see that actually the local maximum is below the local minimum. But keep in mind that these ideas of maximum and minimum are really local ideas. This means that around here, around -1, there is no x such as f goes, f of x is greater than -2, and around 1 here, there is no such x that f of x is less than 2. So this is it. This is the most common way to find the turning point using a critical value table. We are now going to look at an alternative method when you can't factorize the derivative and you have to work on inequalities to do so. So let's do this. Let's work with the inequalities on these 4 intervals here we talked about earlier. These 4 intervals, by the way, can be found, in the 4 columns in our critical values table. So let's see, starting from x is less than -1, what we can say about the derivative. To do so, we'll have to keep in mind the shape of 2 important graphs, the graph of y equals x squared, which is roughly like this. It's just important to remember that it's decreasing on negative part of the x-axis and increasing after that, and y equals 1 over x, which looks like that. It's decreasing for the negative and the positive part of the x-axis. So starting at x is less than -1. Let's square both sides of this inequality. This means that we are going to apply the function f of x is x squared. We see that x is less than -1, so we apply the function on this part here of the negative x-axis, where the function is decreasing. This means that we need to switch the inequality. We get x squared is greater than 1, which makes sense when we think a little bit about this parabola. Let's now take the reciprocal. So we are going to apply the function 1 over x on both sides of this inequality. You see that now this is applied on an interval where we are beyond 1, where the function is actually decreasing. So we'll have to flip again the inequality to get 1 over x squared is smaller than 1. Let's now multiply by -1 to get -1 over x squared is greater than -1. And you can notice that here we've switched again the inequality because we multiplied by -1 on both sides, which is a negative number. And let's finally add 1 on both sides to get 1 minus 1 over x squared is greater than 0, which basically means that f prime of x is greater than 0, which means that it's positive when x is less than -1, which is consistent with what we found here. You see, f prime was positive when x was less than -1. So you see, this is a bit long because we need to repeat these 4 times, but it's actually really handy to apply this method because for functions that don't nicely factorize, such as this one, well, you have no other choice. It's interesting to notice that here we conveniently get to f prime of x is greater than 0. We're actually comparing the derivative to 0, so we can say whether it's positive or negative, and this would have been completely different if we had another number here. But this is something you could have actually expected, because this -1 here came from solving f prime is 0, right there. And you can check that actually the steps that we have here to get from x to f prime are the inverse step of the one we had to get, from f prime here down to x. So we're basically repeating these steps the other way around and just making sure that we correctly switch or don't switch the inequality for every step we take. Okay, so let's now apply the same method on the other interval. So on this interval we get, and here is what we get. You can notice that one dangerous step here, when we try to take the inverse of 0, so 1 over 0 would be infinity, but this is definitely not something that you want to write in an exam. It was just to show you that from this point onward, what we have here, is not really variable information. Okay, a number being less than infinity, we basically drop this side of the equality in any further working. you see we end up with f prime here being less than 0, which is consistent with what we had here in the critical value between -1 and 0. Again, the steps are exactly the same. You can see that we end up with an inequality here that is the inverse of this one, because we started, you know, with the same terms here and there, but just the inequality was oriented the other way around. So in the end, we get the same things on both sides with the inequality oriented the other way around. Okay, so once you've done it once, it's actually no big deal to repeat it a second time. It's extremely similar. Let's now see what we get for the last two intervals. Here is what we get for the third one. So let's see a little bit what went on here. From here to there, we've applied y equals x squared on the three terms of the inequality. You see that between 0 and 1, our curve here is increasing. So we didn't switch the inequalities like we did here and we did there when we were on the negative part. From here to there, we've applied f of x is 1 over x everywhere. So here we've dropped, for similar reasons, what we did here. We dropped this side of the inequality. We still switched this inequality because this function is decreasing here between 0 and 1. Then we've multiplied by -1, thus switching again the inequality, added 1 on both sides to end up with f prime has to be negative, which is consistent with what we have right there in our critical value table for x between 0 and 1. Finally, here is what we get on the fourth interval. I let you check for yourself that the working out here is correct. We get f prime is positive, which is consistent with this part here of the critical value table. In the end, we get the same picture of a function going up when x is less than -1, down between -1 and 0, down again between 0 and 1, and up when x is greater than 1. This means that we can expect a maximum right here, you know, at -1, and a minimum right there at +1, similarly to what we did for the critical value table. So this is it. We've found the turning points and we've characterized them as minimum and maximum. I still have a few comments to make, but you know, here we've seen pretty much the whole thing. This second method here is a bit long, but if you get used to it, that's okay, because you're just repeating a few times what you did when you look for the stationary points, the point where f prime was 0, and you can notice that this function f here has one particular property that we haven't discussed yet, and that's the important fact that f of minus x is minus x plus 1 over minus x, which is minus 1 over x, that you can rewrite as minus f of x. It means that this function is an odd function. What does it mean, again, graphically, to be an odd function? Well, it just means that, let's say, if you draw the graph for the positive side, so if you get something like this, you just need to rotate this graph 180 degrees to get the equivalent of the negative side. We have rotational symmetry of the curve of this function. So what does it mean, really? It means that, you know, half of what we did right there was completely useless. Because using this symmetry property, well, you know that when x is positive, so let's say on this part here of your domain, if you get a function that goes like this and like that, well, you know that if you rotate this graph by 180 degrees, you will end up with something that looks like this. So it's always worth, you know, checking for such property in a function at the beginning and make sure that in your end result you have something that is consistent with such a property. I'm going to add a little video about how to sketch a more accurate graph for this function from the two components x and 1 over x. So check it out if you're interested.